Okay, here the recording in progress. Okay, we're actually up to 11.7 already. So I'm a couple of days ahead. Originally, we were on the schedule to start 11.6 today. I'm finished with 11.6. 11.7 is just a review section. So we're a couple of days ahead. That being the case, I can afford to slow down and probably end early. In fact, most of the rest of the semester, we may be ending early. There are buffer days here and there also, so we'll see how it goes. Okay. So 11.7 is just a review of all the previous sections. And here we go. So the homework is 1 to 33 odd. Let me get those to you presently. I may have shown this to you the other day also, but that's fine. Page 746, test for convergence or divergence. So major topic for this chapter, obviously, as you can tell. Okay. That and that. Okay, so this is strategy for testing series. So these are things to look for. Page 744. One of the things about working problems with series is it's not formulaic. You can't just say, oh, I automatically do this or whatever. You kind of have to look at the series and based on information that you know, decide, okay, should I do this test or that test or whatever the case may be. So here's a little summary of things you can look for. It's up to you if you want to put this on your cheat sheet, you may. Okay, again, I'm raising the book up against the arm of the document camera, so I have to raise it up quicker. Number one, if you see something of the form summation 1 over n to the p, that's a p series, right? P for power. Okay, that convergence of p is greater than 1 and divergence of p is less than or equal to 1. So summation 1 over n squared, n cubed, and to the fourth, those converge. Summation 1 over n, and by the way, if you get summation 1 over n, you should not say it's a p series, you should say it's a harmonic series. Okay, but also summation 1 over n to the half, n to the third, and so on, those will diverge. Number 2 is a geometric series, something of the form a r to the n minus 1 or a r to the n. Okay, geometric series that converges if absolute value of r is less than 1. That means r is between minus 1 and 1. Diverges otherwise. Okay, now 3, and there's no way I can make 3 look nice while holding up the book, but this is the best I can do. It may not be a p series or geometric series, but it kind of looks like it, or you should ask yourself what happens in the long run. In the long run, does it behave like a p series? In the long run, does it behave like a geometric series? In which case, you can try one of the comparison tests. Okay, so comparison test or limit comparison test, as the case may be. Top of 745. Number 4, if you see right away limit n approaches infinity of a sub n does not approach 0, then the test for divergence should be used. Okay, and I emphasize something else about the test for divergence because some of you missed this in the quiz. Okay, test for divergence cannot be used to show convergence of a series. Okay, so a sub n, the a sub n's, the individual terms do not approach 0. The series diverges by test for divergence. However, limit n approaches infinity of a sub n equals 0 does not automatically mean the series converges. And our basic example for that is the harmonic series. The summation of 1 over n. 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5. Those individual terms do approach 0, but the series actually diverges to infinity, in fact. Okay, 5, if you see that -1 business, okay, then alternating series test is a good possibility, right? See -1 to the n minus 1 or -1 to the n, and the n minus 1 or n plus 1 or n, that index is just to figure out, am I going to start with a positive or a negative? Okay, ratio test was a biggie. Okay, if you see factorials, ratio test is usually good for it. Okay? Often other powers. And let's see. The ratio of a sub n plus 1 to a sub n in absolute value approaches 1 for all p series. So you don't want to use that for rational or algebraic functions of n. Okay, ratio tests would generally fail. Okay, if you can see that you can easily take the nth root, then the root test. There aren't that many problems that involve the root test. You'd have to see something just like that. And finally, integral test. If it looks like you can integrate the function, in series you normally use n or sometimes k. When you integrate, switch over to x. And some of you are putting infinity as a limit. You're not supposed to leave infinity as a limit. I will dock you for that. It's supposed to be integral from 1 to b and take the limit as b equals to infinity. Okay. Notice they put this last, and that's because it's the most amount of work. For the integral test, you actually have to integrate. It's more work. So the integral test, I suppose, is a last resort. It's much better to try, one of these other ones we have going on here. Okay. So here we go. So this is 11.7. Okay, so this is page one star. Forget the page. The page is wrong. But it's okay. Summation 1 over n plus 3 to the n. Okay, what does it look like when n gets big? Okay, when n gets big, this is insignificant. 3 to the n is much bigger. Like, which is bigger, 10 or 3 to the 10th? 3 to the 10th is much bigger. So this drops into insignificance. So the comparison series is summation 1 over 3 to the n. All right, so we're doing a limit comparison test. Anytime you do the limit comparison test, you take the limit of the ratio, limit is n approaching infinity, of either this one divided by this one or the other way around. It doesn't matter. So 1 over n plus 3 to the n over 1 over 3 to the n. Multiply top and bottom by 3 to the n. This will cancel out. So limit is n approaching infinity of 3 to the n over n plus 3 to the n. This is infinity over infinity, which means L'Hopital's rule applies. Derivative of the top, derivative of 3 to the n is 3 to the n ln 3, you might recall. Derivative of the bottom is 1 plus 3 to the n ln 3. That, once again, is infinity over infinity, although you can kind of tell, the ratio is going to be 1. The 1 is insignificant in the long run. But if you really wanted to force it, take the derivative again. You have 3 to the n ln 3 times another ln 3 squared. Derivative of the bottom is the same thing. So the ratio is 1. Okay, so limit comparison test says if the limit of the ratio of these two is any positive quantity. There's a lot of positive quantities. The only restrictions are not 0, not infinity, and exists. So the only situation where you cannot use the limit comparison test is one of those. The limit doesn't exist, or the limit of the ratio is 0 or infinity. Okay, and what do I know about this series, summation 1 over 3 to the n? That's a convergent geometric series. The common ratio is 1/3, and 1/3 lies between -1 and 1. Okay, how do I know this is geometric? Just try some of the terms. 1/3, 1 over 3 squared, 1 over 3 cubed, 1 over 3 to the 4th. So you say, what happens? Well, I just keep multiplying by 1/3. Okay, and I see the screen just got frozen again. So I have to take a timeout. But anyway, if you can see the bottom there, I can't point it, but the bottom lower left-hand corner, the series S, it's covered by the pen there, but the series also converges by limit comparison test. So just in case I'm never able to log back on, it says behind that pen, lower left there, S also see the original series also converges by the limit comparison test. Okay, so now let me stop the share and try to get back in. So this might be a while. Mini break. I have to do this. And this. This. Okay, and I think we're back in. Okay, so let me show that to you again. Yeah, here we are. Okay, so the series also converges by limit comparison test. All right, and let's see. I will give you some hints for some of the others. I'm going to do 11. I'll show you some of the others. Number 3, you should be able to guess what to do. That should be a giveaway. Alternating series test. Okay, so if you want to just jot down in your notes, AST. Your number 1, what's a good comparison series? In the long run, what can I ignore for number 1? -1 plus 1. So what's n squared over n cubed? 1 over n. So I would compare it to the harmonic series. So limit comparison test, alternating series test. Okay, this has powers. So for powers, a good thing to use is ratio test. So 5 looks like a ratio test. 7. First thing you notice, n equals 2. What's wrong with n equals 1? Well, natural log of 1 is 0. I'd have to divide by 0. I don't want to do that. Okay. Do you remember what's the derivative of natural log of x? Derivative of natural log of x is 1 over x. So this one looks like a good candidate for integral test. So I would do integral test for this one. 9, there's a factorial. Looks like ratio test is good. Yes, it's alternating, but we have to contend with this. So ratio test, and remember when you do the ratio test, you have absolute values, and there's a -1. You can just ignore that because the absolute value of -1 is 1. The absolute value of 1 is 1. So ratio test for this. Okay, so those are some hints for some of these. Okay, so number 1, LCT, limit comparison test to summation 1 over n. Alternating series test, AST. Ratio test, integral test, ratio test. Okay, so my hint for that one. Let me do 11 in its entirety. Okay, summation 1 over n cubed plus 1 over 3 to the n. So this one you want to break it up into 2. Split it into 2. Summation 1 over n cubed plus summation 1 over 3 to the n. Okay, so I'll have S is equal to S1 plus S2, right? Interestingly enough, we're not even going to find S1, and we're not going to find S2. We just want to say that this converges. This converges. That means real number plus real number is a real number. S1 is our P series. That's our basic P series type summation of 1 over n to the P. It's a convergent P series. So P series where P is equal to 3, that's greater than 1. So S1 converges. You might say, what does it converge to? I don't know. Okay. So a lot of times we will be left with that conclusion that the series converges, but we don't know what it converges to. Don't worry about it. S2 is 1 over 3 to the n. And we just talked about that back over here. That is a convergent geometric series. That one you can actually find a sum. We have a formula for that, right? A over 1 minus r for a geometric series back in section 2, I think it was. And for a convergent geometric series, the sum was a over 1 minus r. But right now, we just want to say it's convergent. And the reason is, you always want to state your reasons. If you don't give a reason, I will take off points. Geometric, common ratio is 1/3, r is between -1 and 1, or absolute value of r is less than 1. Okay. So therefore, the original series is convergent because it's the sum of 2 convergent series. Okay. This is convergent, i.e. it's a real number. We don't even know what the real number is, but it's a real number. This is convergent, therefore it's a real number. A real number plus a real number is a real number. Okay. That's how to do that one. Okay, 13. Summation 3 to the n squared over n factorial. Ratio test is good for factorials. Okay, as I mentioned to you, for problem number 9, I will do the ratio test. Okay. I'll do one of the ratio test problems for you right now. Here we go. So look back in the notes that we just talked about. I don't feel like lifting the book back up because it's heavy, but factorials are almost tailor-made for the ratio test. So a sub n plus 1 over a sub n. Okay, so remember how the ratio test works. Keep this orientation, except everywhere you see n, make it n plus 1. So 3 to n plus 1 in parentheses squared over n plus 1 factorial. And do you remember what happens on this side? If I divide by a sub n, divide by the original, just quickly multiply by the reciprocal. So I flip this, n factorial, 3 to the n squared. And then I combine like items, n plus 1 squared over n squared. I write it like this, n plus 1 over n squared. What do I have for the 3 stuff? 3 to the n plus 1 divided by 3 to the n is 3. And then what do I have for the factorial stuff? N factorial, n plus 1 factorial. This means 1 times 2 times dot 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 times n. 1 times 2 times dot 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 times n plus 1. So everything will cancel out except an n plus 1 in the bottom. Okay, so now what happens when n gets big? This thing right here approaches 1. It's like in a million. 1,000,001 divided by a million, that's 1. Squared is 1. And then times this thing, well, the bottom wins. So this approaches 0 as n approaches infinity. Therefore, the series is absolutely convergent and therefore convergent by the ratio test. Okay? So we went for absolute convergence. Absolute convergence implies convergence. So this series converges by the ratio test. Okay, 15. It's a little bit funny. 2 to the k minus 1, 3 to the k plus 1 divided by k to the k power. Now, you kind of want to do the root test. There are roots. By the way, it doesn't really matter if you have k or n. There's a few problems that the text uses k instead of n, but it's the same thing. I would like to force all of these to be k. This is a k minus 1. This is a k plus 1. So what do? The trick is just go ahead and put the k and then compensate. Okay, so what do I mean by that? It's like, I want this to be 2 to the k. I just put it. So it's almost like I'm cheating, but then I quickly uncheat, if I can coin such a word. Okay, I want the exponents to be k. So I put 2 to the k. Now, how do I make it fair, quote unquote, to be k minus 1? Well, I just divide by 2. Right? So this thing that I have circled here, that is 2 to the k minus 1, is it not? 2 to the k divided by 2 to the 1. And then I play the same trick for 3 to the k plus 1. I want 3 to the k. I just put it. And now how do I account for the plus 1? I multiply by 3. Because this is now 3 to the k times 3 to the 1, 3 to the k plus 1. Okay? So I contend that this whole thing is the same as the original, right? There's 2, okay, right here is 2 to the k minus 1, right? 2 to the k divided by 2 to the 1. And right here is 3 to the k plus 1. So it is equal to the original. Now I separate out the 3 over 2. So the 3 halves can come out. You're allowed to take constants outside of a summation. And now all the exponents are k. 2 to the k, 3 to the k, k to the k power, which now allows me to put the whole thing raised to the k power. It's 2 times 3 to the k over k to the k. So it's like this, right? You're allowed to distribute. K goes here and also here and here. And that comes out to be 6 over k raised to the k power. And now this is a perfect example of doing a root test. It's easy to take the kth root of this thing. Okay. So the next step, you say, what about the 3 halves? Multiplying by a constant doesn't affect convergence or divergence, right? So if this thing converges, it's a real number, right? Multiplied by 3 over 2, it's a real number. If this thing diverges, you don't get a real number, then it doesn't make sense to multiply by 3 halves. That is meaningless. So the 3 halves doesn't affect convergence or divergence. Now I want to take the kth root of that, which is very easy. So root test says take the kth root of absolute value of 6 over k to the k. These cancel out. So I have absolute value of 6 over k. And what happens to that? That approaches 0 as k approaches infinity. Therefore, the series is absolutely convergent and therefore convergent by the root test. Okay. So that's the way it goes. Okay, 17 is another one of those weird factorial things. It goes 1 times 3 times 5, dot, 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 times 2n minus 1, divided by 2 times 5 times 8 times dot, 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 3n minus 1. So it's not really a factorial because we're see factorial is 1 times 2 times 3 times. Here it looks like you jump to only the odds. This, I don't even know what you call it. You start with 2 and you multiply by the number that's 3 above it. So 1 times 3 times 5, dot, 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 2n minus 1. Okay. Double check. If you plug in 1, you get 1. If you plug in 2, you get 3. If you plug in 3, you get 5, and so on, right? Here, if you plug in 1, you get 2. If you plug in 2, you get 5. Plug in 3, you get 8, and so on. Okay. So this is really weird. It's a factorial-like object. So I'll still do the ratio test. Okay, so absolute value of a sub n plus 1 divided by a sub n. Okay, so here, change that to 2 parentheses n plus 1 minus 1. 1 times 3 times 5, dot, 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 2 n plus 1 minus 1. 2 times 5 times 8, dot, 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 3 parentheses n plus 1 minus 1. And then this word thing, just flip it. So the top is the 2, 5, 8 stuff, and the bottom is a 1, 3, 5. That's a 5 there. 1, 3, 5 stuff. Now comes the tricky part. Algebraically, this is 2n plus 2 minus 1, 2n plus 1. Algebraically, this is 3n plus 3 minus 1, 3n plus 2. So what's the factor just before 2n plus 1? I notice these are all 2 apart. So the one just before it must be 2 less than 2n plus 1. What is 2 less than 2n plus 1? 2n minus 1. Similarly, let's look at 3n plus 2. How far apart are these guys? 3 apart. So the factor just before 3n plus 2 is 3 less than that. So 3 less than 3n plus 2 is 3n minus 1. Okay, so again, it's just following the pattern. So I replace this n with n plus 1 in parentheses. It's equivalent to this. I replace this n with n plus 1, comes out to be 3n plus 2. Therefore, the one just before this one, the factor just before this is 2n minus 1. Factor just before this is 3n minus 1. And all of these cancel out. And all of these cancel out. Very nice. So I just have this. And yes, you could do L'Hopital's rule here. I'll let you just jump straight to it like I did here. That approaches 2/3 as n approaches infinity. Right? When n is super big, the plus 1, the plus 2 are meaningless. Just about. So therefore, the series is absolutely convergent and therefore also convergent by the ratio test. Okay. All right, so that was interesting. 19 was going to be the last one I was going to do. Then I'm done for the day, folks. I can do more tomorrow. Summation 1 to infinity, -1 to the n, ln over radical n. Okay, this should be a giveaway as to looking for alternating series test. Right? Side note, but you might think I start with a negative, but if I put 1 or if I put 2, it's actually the same thing. Because what happens when you plug in 1? ln 1 is 0, so the first term is 0, so you don't contribute anything. They could have just started with 2. But anyway, that's beside the point. So I know it's alternating, but what has to be true for alternating series test? It's alternating. The terms have to decrease in absolute value and approach 0. So I have to prove that this approaches 0. So what's the limit as n approaching infinity of ln n over radical n? That's infinity over infinity. So I can do L'Hopital's rule. Derivative of the top is 1 over n. Derivative of the bottom, that's n to the half, right? So the derivative is 1/2 n to the negative 1/2. Okay, I decided to multiply top and bottom by 2 radical n to cancel the 2 with a half. And n to the negative 1/2 means 1 over radical n. Right, so I multiply by radical n over radical n. This whole denominator cancels out. So I now have 2 radical n over n. This is n to the half. This is n to the 1. So I can rewrite it as limit n approaches infinity of 2 over radical n. And you can see this does approach 0, indeed. Okay, so yes, indeed, the series does converge by the alternating series test. It's alternating. The terms decrease in absolute value. That means absolute value of a sub n is decreasing and a sub n approaches 0. So when it comes to an exam or quiz or homework, for alternating series test, you can always write the same language. It's alternating. Absolute value a sub n decreases. Decreases means arrow down. A sub n approaches 0. Okay, and incidentally, a side note, that also means what? That means radical n goes to infinity much faster than ln n. So the square root function is more powerful, I guess, than natural log. So this goes to infinity, but much, much slower than square root function. Okay. All right, folks, I've done what I wanted to do for today. I'm not finished with the section. I was going to continue with the section tomorrow. I'm a couple of days ahead. Okay. In fact, I was planning on the original schedule to finish 11.7 Friday. Looks like I'll finish even tomorrow. Okay, so it looks like we're a couple of days ahead, in which case we're going to end early, as that may be. So let me see if anybody has any questions. I'll check the chat. For 19, could we have just plugged in values and proved the same thing, or would we be required to solve the proof? Okay, you can plug in values just to get a feel for it, right? But the actual proof would be to do all this stuff. Okay? So plug in values kind of gives you a feeling of it, you're right, but it does require proof. Okay, so that's what you want. That's how you should handle this kind of problem. Okay? Now, if all else fails and you can't tell what's going to happen, or L'Hopital's rule doesn't apply, can't figure it out, then you have no choice but to go ahead and just plug in values. Okay. All right, so let me stop the share and see if there's any other questions in the chat. Okay. All right. Any other questions? Otherwise, we're done for the day, folks. All right. Have a good day, and we'll see you next time. Okay. All right. Bye, everybody.
Thank you.
Thank you.